pleasure for me to be here. Vielen Dank für die Einladung. And I would like to start my presentation on limits of the circular economy and key aspects in the eco-design of vehicles. This will be the outline of my presentations. First of all, we will talk about basic principles of thermodynamics. Then we will talk about, or we will question ourselves, whether the green and digital transition can be done the way that we have thought. Then we will question ourselves the circular economy and some final reflections. So let's start with some basic principles of thermodynamics, and don't be afraid, this will be very easy, I promise. And since I am a thermodynamicist, our goal was to understand the value of scarcity, because if we think of the value of things in terms of mass, well, it is clear that 1 ton of iron is not the same as 1 ton of lithium or cobalt. And then when we speak about value in terms of monetary terms, well, money is very arbitrary, volatile, and is not universal. Therefore, we question ourselves, what is the value of scarcity? And in fact, we value that which we find difficult to attain. The improbability of finding things, the uniqueness, the distinction from commonness make things valuable. And this is something that can be measured through the second law of thermodynamics, through exergy property. Imagine that we have a ball on the top of a hill, and we push the ball a little bit. What will happen? Well, it will go down irreversibly until it reaches the ground, until it reaches what we call the dead state. Now, imagine that with that same amount of energy, we would like to put the ball again on top of the hill. That would be impossible. So falling down is very easy, but climbing the hill costs exponentially more energy. And this translated into materials, the height is purity. So the higher the ball, the more useful things we can do with that difference in height. And in material terms, the purer the element or the mixture, then the more quality it has. But if we mix, for instance, if we have sugar and salt, by themselves they are very useful, but if we mix them, then the mixture is not useful anymore. And demixing it costs a lot of energy. So the first lesson of thermodynamics, which is related to exergy, is that everything that differs from the surrounding environment, from that ground, has exergy, has quality, has usefulness, and it depends on both, on the height and on the ground. So the corollary to this is that each mineral can be characterized through exergy with a single unit of measure in terms of energy, like kilojoules, for instance, or ton of oil equivalent. So the height would be the purity, and the ground would be the crustal concentration, which is the total dispersion of raw materials. So in this sense, we can quantify, which is what we call the thermodynamic rarity of minerals, which is a measure of the physical criticality of raw materials. And in this periodic table, you can see here those elements marked in red, which are specifically very critical from a thermodynamic point of view, whereas those in green are more abundant and easier to extract. The second lesson, which is related to the second law of thermodynamics, which is truly the most frightening physical law in what exists in nature, is that all natural and man-made processes tend spontaneously to degradation. And the way back is very costly or even impossible. So the corollary to this is that mixing is the most entropic process that exists. Keep purity as much as you can. Now, towards a green and digital transition, let me give you some figures. Nature's depredation is growing at a rate of about 2.8% per year. What does this mean? It means that in one generation, we will consume twice as much as we do today. And in 25 years, we will have consumed as much as in the whole history of humanity. But this is not future, this is present. I can tell you that during the 21st century, in 21 years, because there are records until 2021, more or less, we have consumed as much copper as in the whole history of humanity. And this repeats for many commodities. For instance, gold, which is very used in electronics, obviously also in jewelry, we have consumed 0.5 times as we have records. Silver, used very critical in solar energy, electronics, jewelry, 0.6 times. Zinc, used in steel, in metallic parts, 0.8 times. Nickel, absolutely critical for batteries, and for steel, obviously, 1.2 times. Cobalt, 1.56 times, and lithium, almost 2 times. So I am sorry, the shortage of raw materials and supply disruption is not a one-off issue. It is a truly structural problem. And what is the consequence of this exponential extraction? Well, we have done studies several years ago analyzing the different commodities that are essential for the green and digital transition. And what we got is that the production peak of most essential minerals for this transition could be reached before the end of this 21st century. And I am talking here about resources, about amount of raw materials which are not available today, which might be available in the future if technology improves and if we explore further, etc. Considering what we can extract today, which is the reserves, the result is that most or many of the resources have already reached its peak. And you might say, well, the Earth is still to be explored, and we will find further reserves, further mineral deposits, and this is true. We will find and we will exploit further mineral deposits. However, let me show you another study that we performed back in 2017, where we see here the example of lithium. We analyzed, depending on the reserves, the available reserves or resources, which would be the peak. Now, the least optimistic data regarding the reserves that currently exist gives us a peak in 2032. Then we have other studies that says, no, it's not 31 megatons, it's about 40 megatons. That displaces the peak just 5 years to 2037. If we go to the resources, then the peak is by 2049. If we doubled the resources, we get 2060. And if we go to the lithium of the seas, we have 2078. So as you see, it is not the quantity that we have in the ground, which will increase for sure, but it is this exponential increase of demand that will cause supply disruptions. And this has another consequence, which is also related to thermodynamics, to the second law of thermodynamics. Here, let me show you some figures where we analyzed thousands of mineral deposits of copper, gold, or zinc. And what we did was to analyze the ore grade, the concentration of the minerals in the mine, versus the energy required to extract. Now, what you can see here is just a consequence of the second law of thermodynamics. When mines become depleted, the energy required to extract the next ton of material tends to infinity, is exponential. So, and I have to give you bad news. Energy for mining is mostly based on fossil fuels. In open pit mining, we have very large, very big trucks which are transporting all the rocks, all the waste rock, and then it is sent to the further refining processes. And it needs a lot of energy. So if we are going to need more materials, if mines get depleted, then energy will increase, and if this energy comes from fossil fuels, and it is very difficult to electrify mining operations, then GHG emissions, at least associated to mining, will increase. And this is not contemplated in current scenarios of energy transition. So talking about scenarios, we did, a few years ago, we did an analysis of the International Energy Agency scenario, the 450 scenario, analyzing how will be the energy, or let's say the exergy reduction related not only to energy resources, but also to mineral resources. And obviously, the energy associated to fossil fuels will decrease, but this will be done at the cost of increasing the exergy, the quality of raw materials. So here we saw that the energy dependency will be shifted towards a material dependency. Why? Because clean technologies requires a huge amount of raw materials, and not only in quantity terms, but also in quality terms. A lot of different raw materials, which are very, very scarce. For instance, you can see by 2050, the share of the electric vehicle, which will be very important, also of hybrid vehicles, bioenergy, or solar photovoltaic, versus conventional technologies, which only account for 3%. So material bottlenecks in the future. Yes, there will be, as you have already noticed. And we analyzed for this energy transition, and considering the different clean technologies, we analyzed in 2017, it was published in 2018, considering the reserves, whether we would find bottlenecks of raw materials. And what we saw was that by 2050, demand could be greater than reserves for silver, cadmium, cobalt, chromium, copper, gallium, indium, lithium, manganese, nickel, lead, platinum, tellurium, or zinc. These elements are essential for the clean transition, and these elements are especially essential for electric vehicles. And with a study that we performed together with SEAT, what we saw is that there is a good amount of materials which will be essential for the automotive sector, and there will be really risks in the supply. And we're talking about other materials like tellurium, terbium, antimony, dysprosium, nickel, lithium, lead, and so on. So there are, I'm sorry, but there are mineral limits to the green ecological transition, and this is a fact. But it's not only about the green ecological transition, it's also about the digital transition. Here you can find a study that we performed also with SEAT, analyzing the rarity of the elements that are contained in different technologies. And we include here also the vehicle, because the vehicle is a computer on wheels. But if you look into the materials that it contains, it is also a mine on wheels. And the same happens with computers, obviously on a smaller scale, tablets or phones. And let me show you a study that we performed together with Wuppertal Institute quite a long time ago, but the message stands. And we analyzed different appliances, different electric and electronic equipment, analyzing the rarity, the physical criticality of these materials, of these appliances. And what we saw is that more efficient technologies are in fact less efficient from a material point of view. Yes, and this is not only for electric and electronic equipment, it is also for vehicles. Here I show you Project Excite that we did together with SEAT, analyzing different, not electric vehicles, but internal combustion vehicles, and what we saw is that in mass terms, most of the vehicle is composed by iron, aluminum, and copper. And this is helpful because if we focus only on the recycling of these three materials, then we would comply with the legislation, which is 95% of the car needs to be recycled or valorized. However, if we look into the materials in terms of rarity, what we see is that the internal combustion vehicle is, has a rarity which is much lower than the electric vehicle. Because it contains very critical elements such as cobalt, as you see, lithium, nickel, tantalum, and others. Obviously, you are already reducing the amount of such raw materials, maybe not because they are thermodynamically rare, but common sense tells you we should reduce cobalt. And the different generations of batteries, we see NMC 333, 622, or 811, reduces effectively the rarity of the different electric vehicles. But it's not only the battery, it's all the electrification of the vehicle, which contains very rare materials. This study was performed just a couple of months ago in our institute, and we analyzed different SEAT models, starting with SEAT 600 back in 1955, until Cupra Born, which is today's model. And what we saw is that the energy efficiency of all models have increased a lot, really a lot. However, the material efficiency has decreased exponentially. The rarity has increased a lot. And this, we need to do something about this. So there is a new alarm sign now, and everyone is very worried about this issue. It is not an academic problem anymore. It is a real problem faced by the automotive industry and by many industries. And there are critical materials for the EU. Lists of critical materials, which nowadays contains more than 30 elements. And I remember the first list 10 years ago, which contained only 14. So every 3 years, which becomes this list updated, the number of materials increases. Why? Because we are exponentially demanding more and more raw materials. So what do we have to do? We need to move towards the circular economy. Okay, but obviously I come from academics, and we question ourselves, we question everything. So towards the circular economy. Let me tell you that there is what we call chemodiversity in common products. What is this? Increasingly complex products and materials with better functionalities, which with lower weights, for instance. However, the result is that there are many scarce elements in common products which are difficult or impossible to recycle. You see there the case of a mobile phone. And what does this imply? This implies that this mixology, this mixing of sugar and salt and many other components, implies irreversible losses at the end of life. This is the well-known metal wheel, which was developed by our colleague Markus Reuter and colleagues, in which we see that if we go through the iron route, for instance, if we want to recover steel, then you will lose many other critical elements underway, for instance, copper or rare earths, etc. So I am sorry, there is no circular economy. So you might call this session the spiral economy. Because in every cycle, we lose a little bit. And this is a consequence of the second law of thermodynamics. The third cycle, the fourth cycle, the fifth cycle, and the losses become larger and larger. But obviously, we should aspire to try to close the circles as much as possible. And we're still very far removed from that end. And I tell you why. Focusing on the car, there are no specific recycling operations to recover scarce and valuable metals from end-of-life vehicles. If we, at the end of life of a car, we send the car to a shredder, and then through very basic physical operations, we get three groups of materials. First, ferrous metals, non-ferrous metals, and waste that usually become landfilled. So over 15 different alloys end up as low-quality materials. What we're doing is we're mixing all types of steel, for instance, and we're melting them. Now, if you mix good wine with bad wine, what do you get? You get bad wine. Well, this is what we're doing currently with recycling processes in cars. Because it needs about 2 days to manufacture a car, but only 30 seconds to recycle it. And I told you the difficulty in really recycling, in really recovering the materials. And if you analyze, in terms of rarity, the materials that really become lost, at least, and I say at least, a minimum of 1 out of 4 cars, in terms of rarity, become lost at the LOA end of life. And this, taking into account that the legislation is telling us that 95% of the car needs to be recycled, and we are complying with that figure. So, seeing this problem, we, together with SEAT and with Helmholtz Institute Freiberg, we analyzed the recyclability of cars, dismantling different parts of the car, and then we designed very complex recycling processes, not the processes that currently exist, but very complex metallurgical processes optimized to recover all such materials. And this was 124 units operations, over 500 streams, and analyzing 50 elements. So focusing, for instance, on the non-ferrous fraction, we saw that we could recover a high quantity of, for instance, precious metals or base metals. However, other metals would be recovered in just 50%, for instance, germanium, indium, or tin, and many other metals would become lost in slags. And we're talking about very critical elements such as rare earths, lithium, tantalum, chromium, titanium, etc. So, how to make the car more circular? This is one of the objectives of the project Treasure, in which we are involved together with SEAT and many other partners. And what we are trying to do is to connect all the shareholders of the car industry through a platform, so that designers have feedback from dismantlers and the way around, and we can optimize the circularity or the spirality of the process. And here you can see, for instance, this is a prototype of the eco-design module where we see the metal use, the plastic use, the disassemblability or the recyclability of different car parts. So final reflections. Energy efficiency or raw material efficiency? I would say both. Both are very important. And let me tell you that I would propose to move towards what I call botijo engineering. You know what is a botijo? Botijo is a clay jack that was used, or that is still being used, not that much, but in many Spanish families in order to drink water. And this shape, and because it is made completely out of clay, makes that it is very efficient. It keeps water cool. It keeps water cool even if we do not apply energy to it to refrigerate it. It has a very simple design. It uses local and cheap materials, clay. It is robust, it is easy to repair and recycle, it has just one material, and it creates a sense of community, of sharing. I remember my whole family, 30 people of us, going to the country house of my grandparents, and we had competitions on who had the largest water jet of the botijo. Unfortunately, today, botijos have been replaced by individual plastic bottles or soda cans. But good news, you know how to do it. Back to the roots, back to the future. Volkswagen Beetle, der Käfer, and if I am not wrong, because I am not from here, but I read this, was the longest lived model ever produced, 65 years. It had quality in the products because it was designed to be as simple as possible mechanically, used a few mostly local and abundant materials. It was robust, manufactured to last. It was easy to repair, parts could be quickly and inexpensively exchanged. It was energy efficient at those times, obviously. Versatile, I read that it used other fuels such as wood in times of war, and it created a sense of community. In fact, we had the pride in the antique, those that had a Käfer, a beetle. So quality in the products, and you know how to do it. But not only quality in the products, we need also quality in the processes. And here I propose la desfábrica, this factory. Because a car factory produces a car every 2 minutes. Yet the same factory is unable to dismantle a single car. In the design of cars, make sure that your production line is able to dismantle that same car. Because we need to move towards a wheel-to-wheel strategy, because for a true circular or spiral economy, the car should not be a source of materials as it is done now. It should be a source of spare parts. So, botijo engineering and this factory, Decalogue. The aim is not to recycle 95% of the car in terms of mass. The aim is to recover 95% of the car parts by thermodynamic rarity, so that the car parts become refurbished and reused. So quality in products and processes, which means dematerialize, use abundant and local materials, designing car parts with low thermodynamic rarity. Maximize the use of raw materials, of recycled materials, designed to last. Concentrate all high thermodynamic rarity car parts, mostly electronics, in a specific spot of the car so that you can facilitate dismantling. Standardize, avoid the use of glues, of welding, and try to mimic the aviation industry, which uses rivets. Avoid the use of complex materials and mixtures impossible to recycle. Understand the thermodynamics and the metallurgy behind all the car parts. Invest, very important, invest in data traceability and data quality. Speak to your providers, speak to your dismantlers, speak to the users, which was the aim of Treasure project. And very important, spare parts reutilization and car parts refurbishing. Because there are many challenges ahead. And I tell you what, greening the car industry by substituting conventional cars with electric cars is not sufficient. Relocalizing tier 1 factories in Europe is not sufficient. Raw material supply alliances with mining nations and companies is not sufficient, simply because there are not enough raw materials. Because access to raw materials will become more and more difficult and expensive, and not everyone will be able to afford a car. Culture is also changing. The car industry needs to reinvent itself. Car leasing and sharing concepts, simple, affordable cars, refurbishing strategies for many car parts, this factory. The age of abundance is over. There is a raw material supply decline. Is this an economic issue that can be solved? I would say no. No with data. Because we are reaching planetary limits. It is about ecology. It is physics. It is the second law. It is our responsibility for the future generations. The sooner we recognize this and work on this new scenario, the better prepared we will be. And the good news is that you know how to do it. Think small. Thanks for your attention.